So, dear students, welcome to the new lecture of Basic Electrical Engineering. In this particular lecture, we will discuss about the EMF equation of the transformer. So, this lecture will cover a basic understanding of the principle of working of the transformer. Then we will discuss about the EMF equation of the transformer, and then we'll see what is transformation ratio. So, let us start with the principle of working of the transformer. Now, as we all are well aware of the fact that the transformer works on the principle of Faraday's law of electromagnetic induction. So, the Faraday's law of electromagnetic induction states that when you have a magnetic field and you have a conductor which is placed in this magnetic field, so this conductor, if moved, if it is in motion, then this conductor will have certain EMF induced on it, and this EMF is given by E is equal to minus d phi by dt, or more specifically it is E is equal to minus n d phi by dt. So that means there has to be a rate of change of flux. Now there are two ways by which we can have this rate of change of flux. Either um, the conductor is stationary, it is static, and the flux is varying, or vice versa, right? That means the flux is static and conductor is varying, conductor has motion. In both the cases, if there is a relative movement between the two components, the conductor and the flux, there will always be an EMF induced on that particular conductor, right? So this is what Faraday's law of electromagnetic induction states. Now in transformers, because transformers are the uh, electrical machines, they are, a transformer is a static device which is used to change the level of the voltage. Either the level of the voltage is increased at output or it is decreased at output. So on that basis we have the two categories. One is the step up transformer, and then we have the step down transformer, right? But as we all know that in transformers, if we have a core basically, and the windings, the two windings of the transformer, means the primary winding and secondary winding, are wound on the two limbs of the transformer in core type transformer. And if we have a shell type transformer, then the two windings are wound on the central limb of the transformer here. So this is in case of shell type transformer. But in any case, uh, the conductors are basically stationary. So the conductors, that is the windings, are static. They do not move. We do not have any moving part in the transformer. Then how do we get the uh, Faraday's law of electromagnetic induction happening in the transformer? So that we will understand. So it is the Faraday's law of electromagnetic induction which is the basis of the working of an electrical transformer. Then there are two types of inductions that take place in the transformer. The first is known as self-induction, then we have mutual induction. Now, what are these two inductions basically? Now, when you have a transformer, let us draw a core type transformer. This is an iron core, and we have the two windings wound on this particular transformer core. One is on this particular limb, and let us say the second is on this particular limb, like this. So this is the primary winding, and this one is the secondary winding, right? Now when you have the current flowing in this primary winding, this current will produces certain flux in this particular winding, and this flux will move in a particular direction in the um, core, iron core, and will link to the another uh, winding of the transformer. This is the secondary winding. So the linkage of this flux with the secondary winding will create some current to flow in the transformer. So this is how the current will be flowing. Now when this current flows in this particular winding, the primary winding, because the current belongs to the primary winding, the supply current flows in the primary winding. However, the induced current flows in the secondary winding, right? So this is the primary current, let us mark it as ip, and this is the secondary current, let us mark it as is. You can take any notation, you can take either I1 or I2, IP, IS, that is totally up to you. There is no thumb and rule for taking a particular type of notation. It is totally up to you. Simply have to distinguish between the two types of notations, right? So when this current will flow in this particular winding, if this is a time varying current, if this is a varying current, then what will happen? This varying current will produces a varying flux in this particular core. Now this varying nature of the current will produces an EMF in this particular winding, which is, let us say, EP, because of the self induction. It is the self induction because of which an EMF will induced in this particular winding at this particular end, right? Now this is because of the self induction. Now when the current flowing in a particular winding induces an EMF in that very winding, this effect is known as self induction effect, right? Now if this flux which is produced because of this current reaches to the secondary winding and links with the secondary winding and produces a current in the secondary winding, and then there is an EMF that induces in the secondary winding. So this EMF is because of the mutual induction. It is because of mutual induction, right? So this, both the types of inductions take place in a transformer. The primary has the self induction. The EMF that induces in the primary is because of self induction, and this EMF opposes the supply voltage. So we will understand this in detail in forthcoming lectures, how it opposes and what is the reason behind it. But it is the self-induction which induces an EMF in that primary winding for to which that primary current belongs. And when this flux, which is because of the primary current, reaches to the secondary winding, links with the secondary winding, induces an EMF which we call as the secondary EMF, and this EMF is induced because of the principle of mutual induction. So in short, we can say it is the mutual induction due to which the EMF is induced in the secondary winding. And because we need the EMF in the secondary winding, because the load is connected to the secondary winding of the transformer, so we need an EMF to be induced in the secondary winding. So we can generally say that the principle of working of a transformer is mutual induction. It is the mutual induction, right? So now let us move further. Now, this is what I was talking about, the self-induction. So when we have the EMF induced in the same circuit, same conductor, because of that same current, so it is the self-induction. And if the EMF is induced in some other coil, other conductor, because of the magnetic field produced by the primary coil, primary conductor, so we call this as the mutual induction. So now this is what I was talking about, because your uh, conductors in a transformer are static. So how are we getting that d phi by dt? Because as per Faraday's law of electromagnetic induction, E is equal to minus n d phi by dt, where this n is the number of turns of the coil, right? And this is the rate of change of flux. So how are we getting that d phi by dt when we have the static conductors, that is the windings in a transformer? So this is the answer to that particular question, because we are using AC supply in transformers. So this AC supply, which is time varying supply, which is bidirectional supply, produces a time varying flux or bidirectional flux in the iron core of the transformer. And this time varying flux, when reaches to the secondary winding, links with the secondary winding, produces a time varying EMF or current in the secondary winding. So having the conductor static, we have the EMF induced in the secondary winding. It is either the conductor moving the static magnetic field, or it is the time varying flux, or conductor is static. So in both the cases, if there is a relative movement between conductor and magnetic field, the EMF will definitely induce on the conductor. So this is what Faraday has suggested. So let us see with the diagram what is self-induction. Now, as you can see in this particular diagram, there is a coil which is wound over an iron core. This is an iron core, and we all know that why it is used. It is used because we know that a ferromagnetic material can conduct maximum flux, because the permeability of a ferromagnetic material is quite high. Okay, so now what actually is happening, you have a battery source, and then you have a current limiting resistance. This is known as current limiter. So it is a current limiting resistance. Now there are n1 number of turns in this particular coil. It is wound over an iron core. Now when the current flows in this particular coil, and the current is flowing like this. So using the right hand thumb rule, if you curl your finger with this one, so your thumb will give you the direction of magnetic flux. So, right. So now there are two things happening here basically, because this is the uh, coil itself, and it has magnetized this particular ferromagnetic material. So this magnetization, this magnetic field, this own magnetic field, will induces an EMF in this very coil, which will oppose the main magnetic field. So there are two magnetic fields basically, and there are two EMFs. One is the supply EMF, second EMF will be induced in this particular coil, and this EMF in turn will generate or produces its own magnetic field, which will oppose the main magnetic field. So that is why you can see there are two types of directions. Like here also you have the exit, the magnetic line of force are exiting this end and exiting from here and entering at this particular end. And you can see here also the magnetic line of force are exiting and exiting from here and entering at this particular end. Now why it is happening? Because the current induced due to self induction will oppose the current due to main source. Now, if the direction of the main current is this one, so the direction of the induced current will oppose this and the direction will be opposite. So when the direction will change, the direction of flux because of main current will be this one and the direction of flux because of the induced current will be this one. So that is why we have both the directions. So this is what self-induction is. We have a coil, the current belongs to that coil, the EMF is induced in that particular coil, and that EMF will opposes the main EMF. So this is what self-induction is, right? So let us see with the diagram what is the mutual induction. Then in this particular diagram, as you can see, we have an AC source connected to the this coil here. This is, let us say, the primary coil. This is the primary coil, and this is, let us say, the secondary coil. So this is how the transformer works basically. So as you can see here, because of this time varying supply, this flux which is generated by this coil which is wound over an iron core is also time varying. So this is a time varying flux. So because this is a time varying flux and it is linking with the another winding, and you can see that both the windings are static. Both these windings are static in nature. They are not moving at all. It is the flux which is varying with time. So there is a relative movement between flux and the conductor. So we have d phi by dt here. So now when this flux is linking with the secondary winding, you can see when it links with the secondary winding to maximum extent, we have the lamp glowing here. So that means the current will flow in the secondary winding if the load is connected. Even if load is not connected, we have an EMF induced in the secondary winding which is at this particular end. So this is what becomes the basis of a transformer. It is the mutual induction. This is what the mutual induction is. So the two windings are not connected to one another physically. They are connected to one another through a mutual flux. There is a mutual linkage between two windings because of this time varying flux, and this is what mutual induction is, right? The current belongs to primary winding, the flux belongs to primary winding, but it is linking with the secondary winding, and EMF is inducing in the secondary winding, current is flowing in the secondary winding, and it is the this is what we call as the mutual induction, or this effect is known as mutual induction, right? So I hope this is clear to you what is self induction and mutual induction. Now, let us come to the next part of the topic. Now, before that, as you can see here, this is a very small symbolic representation of the working of a transformer. It is now here Vp and Ip are the primary voltage and primary current. V is the flux density, magnetic flux density or magnetic field density. So it is, and then Is and Vs are the secondary current and secondary voltage. Now you can see here when Vp and Ip are changing, they are producing a changing flux. So this changing flux is when linking with the secondary winding is producing a changing secondary current and secondary voltage in the secondary winding of the transformer. So this is a very small symbolic. So in this short picture, you can easily understand the working of a transformer. So I repeat, it is the Faraday's law of electromagnetic induction, no doubt, but there are two types of inductions. One is self-induction, which takes place in the primary winding of the transformer, and then there is a mutual induction, which takes place in the secondary winding of the transformer. Means the due to the self-induction, an EMF is induced in the primary winding of the transformer, and due to the mutual induction, an EMF is induced in the secondary winding of the transformer, because we need the current to flow in the secondary winding because the load is connected to the secondary winding. So we can say that the principle of working of a transformer is mutual induction. Now let us come to the EMF equation of the transformer. So now let us discuss about the EMF equation. As I have already discussed with you in previous slide, that Uh, when you connect an AC supply to the primary winding, what happens? Now, before that, let us understand this V1 is the RMS value of the this supply voltage. So either you can use V1 or VP, whatever, it is totally up to you. The notation doesn't matter here, right? Now when the current will flow in this particular winding here, the current will flow like this, and we have, because this is a time varying flux, this is an AC supply. So the nature of this flux will also be AC. It will also be a sinusoidal flux. The instantaneous value of the input voltage is given by Vp Vm sine omega t, and when this voltage, which is time varying voltage, which is time changing voltage, will produces a flux, which is also an AC flux or sinusoidal flux or bidirectional flux. So the instantaneous value of that flux is given by phi is equal to phi m sine omega t, where phi m is the peak value of this phi, the sinusoidal flux. Now, now let us now whether it is self induction or mutual induction, as per the Faraday's law of electromagnetic induction, the EMF induced here is given by E is equal to minus N d phi by dt in general. This is the general equation of that particular EMF. So if we substitute the value of phi from equation 2 in this equation number 3, so we have E is equal to minus N d by dt, and then we have phi m sine omega t, right? So now we can simply solve this equation. So this will give us minus n omega phi m cos omega t. So this would be the equation. Now derivative of this will be this one. Now we can also write, because let us say this is equation number 4, and because we know that cos theta is equal to sine pi by 2 minus theta, as per using the trigonometric rule. So uh, we can substitute it here. So E would be equal to uh, minus n omega phi m sine pi by 2 minus omega t. So we can rearrange, we can take this negative sign common, so this will be cancelled out here. So we can simplify this one. Is equal to n omega phi m sine omega t minus pi by 2. So this is the equation number 5. So the equation 5 gives us the instantaneous value of the EMF induced in the coil, right? Now as you can see here, the nature of this induced EMF is also sinusoidal. It is easily observed, depicted from the equation number 5. So it is a sinusoidal EMF which is induced in the coil. Now let it be a primary coil, let it be a secondary coil. So here, because of self induction, you have an EMF which is capital EP. So capital EP is, I'll write somewhere, I'll write it here. EP is the RMS value of EP. Now this small EP is the instantaneous value of primary induced voltage, and capital EP is its RMS value. Then we have, when this flux moves to the secondary winding and it is a bidirectional flux, it will induce in a voltage which is ES in the secondary winding, and this ES is the RMS value of es, where this es is the instantaneous value induced voltage or emf, right? So now this is what happens actually. So here we have because of the mutual induction, and here we have because of the self induction. Self induction in primary, mutual induction in secondary. So whatever happens, whether it is because of self induction or it is because of mutual induction, the EMF equation will always given by this particular equation number 5. So now uh, simplifying equation 5, so we can write this as E is equal to Em sine omega t minus pi by 2. So this is, let us, equation number 6. So where Em is nothing but it is n omega phi m. So this is the uh, peak induced EMF. So this is the peak value of this induced EMF, E, which is induced in the coil, right? So we have two types of coils in transformer, primary coil and secondary coil. So in both the coils we have similar kind of voltage. So let N1 and N2 are the number of turns of the, or let us say, not let us take it as N1 and 2, let us take it as NP and NS. So instead taking it as N1 and 2, we'll take it as NP, P for primary, S for second, number of turns of the uh, primary and secondary winding of the transformer. Then the instantaneous value of the induced EMF in both, sorry, in both the windings is given by, now it is very simple to write the equations. So EP is the instantaneous value of the primary uh, winding, and this is because of the self induction. Because of self induction, so EP is equal to EMP sine omega t minus pi by 2. This is, let us say, equation number 7. And then because of mutual induction, we have the secondary instantaneous value, which is EMS sine omega t minus pi by 2. So this is, let us, equation number 8. So where EMP and EMS are the peak values of the induced EMFs in the primary winding and secondary winding of the transformer, right? So now let us take equation number, let us take this EM basically. Now this EM is equal to N phi M omega. Uh, this is taken from this particular equation here, this one. So omega we know it is equal to 2 pi f, and em we know that it is under root 2e, because we know that the rms value is equal to peak by under root 2. So peak value by under root 2. So the peak value is equal to RMS into under root 2. So this is the RMS value of the induced EMF, right? So let us simplify this one. So we have root 2e is equal to n phi m into 2 pi f, or e is equal to 2 pi n phi m f by root 2. So this particular part, it is a constant, so this is equal to 4.44. So E is equal to 4.44 n phi m f. So this is, let us say, equation number 9. So the equation 9 is the EMF equation of a transformer, right? So we can find out the RMS value of the primary and secondary separately. So EP is the RMS value of induced EMF in primary coil or winding. Similarly, ES is the uh, RMS value of induced EMF in the secondary winding, right? So EP, now by relating this equation here, so we can have both EP and ES. So EP would be equal to 4.44 N P phi M F. This is, let us, equation 10, and ES would be equal to 4.44 N S phi M F. So this is equal to equation number 11. Now, if you see here, for a particular transformer, generally phi m and f are, these are constants, right? 4.44 is a constant, so we can say that these equations, the EMF induced in primary winding is directly proportional to the number of turns of the primary winding, and ES is also proportional to the number of turns of the secondary winding, right? So if we write it like this, EP is equal to K and P, because you know that this 4.44 and these two, so these are same in both the cases. Here also you can see these three factors are same, right? So ES is equal to K and S, where K is the constant, right? So we can say that this 4.445 m is a constant, right? So EP is equal to K and PES is equal to K and S. So, or you can write EP by NP is equal to K, and ES by NS is equal to K. So we can also write it like this. Uh, So we can write it like this: EP by NP is equal to ES by NS is equal to K, right? So this K is voltage transformation ratio or voltage to turn ratio. So this we will take up in the next slide, right? So voltage transformation ratio or voltage to turn ratio, right? So as you can see here, we have the same equation: EP by NP is equal to ES by NS. So E1 is associated with the primary winding, N1 is the number of turns of the primary winding. Similarly, E2 is the RMS value of the induced EMF of secondary winding, and N2 are the number of turns of the secondary winding. So you can use any notation. You can simply use EP by NP, ES by NS is equal to K. So this is what transformation ratio is. Now, what does transformation ratio signify? It generally gives us an indication of whether the transformer is a step up transformer or a step down transformer. So if the number of turns of the secondary winding are greater than number of turns of the primary step up transformer, so it can be like we have a core type transformer. So the number of turns and the secondary are greater than this one. So this is a step up transformer, and if the vice versa is there, that means number of turns of the secondary winding are less than number of turns of the primary winding, then the value of transformation ratio is less than 1. So this is what we call as the uh, step down transformer, right? So that means a transformation ratio gives us an indication of the uh, whether the transformer is step up or step down, right? A step up transformer is the one in which the output voltage is greater than input voltage, and step down is the one in which the output voltage is less than the input voltage. So now in this particular lecture, we have understood about the various aspects of the transformer. How does it work? What is the principle of working of a transformer, right? Then we have seen the EMF equation of the transformer, and that we have seen that the EMF which is induced in the transformer, the instantaneous value of that voltage is given by equation number 5 as shown here, which is E is equal to N omega phi m sine. So that means the induced EMF depends upon the number of turns, the omega, the angular velocity, and the flux, peak value of the flux here, right? This one. Okay, so uh, then we have seen the EMF equations of the two windings separately by equation number 7 and equation number 8. And finally, the equation number 9 gives us the final equation, EMF equation of the transformer. And from this equation number 1, we can derive the separate equations for both the windings of transformer. And in that, we have seen that 4.445 and the product of these three is common for both the equations. So from here, we can say that the EMF induced in the primary winding, that means the RMS value is proportional to the number of turns of the primary winding, and similarly the EMF induced in the secondary winding is proportional to the number of turns of the secondary winding. From there we have got one factor which we call as voltage transformation ratio or voltage to turn ratio, because this is voltage, this is turns, the voltage to turn ratio, and this indicates whether the transformer is a step up transformer or step down transformer. Now, this is an animated view of Faraday's law of electromagnetic induction. Now, in this you can see when this magnet is a source of magnetic flux. This is a conductor. This is a galvanometer. This is a wire. Wire is a conductor. It is wound over an iron core. This is an iron core, right? So when you're moving this magnet towards this conductor, so this particular end becomes north pole and it repels this one. When you move this magnet away from this iron core or the system, it becomes south pole. This end becomes south pole, and you can make it out from the direction of the current basically, right? So you can see the direction of current is this one, so this is north pole, and when you are moving it away, so direction is downward. So but you can notice one more thing, that when your magnet is stationary, it stops somewhere, so the current becomes zero here. This current becomes zero. Okay, it is only when this magnet is moving. Now why are we moving this magnet? So that we can have the varying flux, we can have that factor d phi by dt. So this d phi by dt is very very important to have the EMF induced in the conductor, and this becomes the principle of various electrical machines including transformer. And this was all about today's class, guys. Thank you so much.